Hi, today we are going to begin our study of Taylor polynomials, which is an extension of our power series or our series that we were looking at before, our infinite series that we looked at last unit. So we're just going to dive in and do a little bit of exploration today before we fully define what a Taylor and a Maclaurin series are. So a Taylor polynomial is a polynomial function that we can use to approximate functions that are not polynomials. So functions like sine of x, cosine of x, e to the x, natural log of x, and others for certain values of x. Now, the polynomial will not be exactly the same value of the function, but it will oftentimes be so close that there really isn't much of a difference. And what you're going to see is the more terms that we add to our series or to our Taylor polynomial, the better the approximation gets. So we're going to start with a little bit of a discovery on how to build a Taylor polynomial. Okay, so we have this graph that is y equals the cosine of x. And I want you to find an equation for the tangent line of y equals cosine of x at x equals 0. So we're trying to find a tangent line, which means we need a derivative. And I need the slope, which comes from the derivative. So let's first find our derivative. So y prime would be negative sine of x. And we're trying to find it at x equals 0. So it would be y prime would be negative sine of 0. Which is 0. And at x equals 0, we have the ordered pair 0, 1. And so my equation for the tangent line would be y minus 1 equals 0 times x minus 0, which means I get the equation y equals 1. So let's graph this line. I'm going to go ahead and sketch this graph, this linear approximation in blue. And so the line y equals 1 is something like this. Now, can we say that this line, mine's not super straight, but can we say this line approximates the graph well? Not really. I mean, at a point, yes, we can. We can say it approximates it really well, but only when x is 0. So at x equals 0, this is a perfect approximation of y equals cosine of x. The problem with that is, if I'm trying to approximate the entire function of y equals cosine of x, this is not a great tool to have. Okay, so what else might we think of? If you were to think of a shape that would approximate this well, or what is this graph lacking that we might need to be able to approximate this curve? Hopefully what you think about is we need some concavity in there. We need the graph to bend and to have some curve. And so if we're talking about concavity, what degree are we looking at? We're looking at a second degree. Okay, so what we have is a constant function. If I want it to bend, I need it to have some concavity, which means I need a second degree. And so let's come up with a quadratic approximation. Let's give it a name and let's call it, I'm going to name it a little bit differently than we're used to seeing. Let's give this some name a subscript 0 plus some a subscript 1, x to the first, plus some a subscript 2, x squared. That's a quadratic approximation. And our goal is to make this quadratic function approximate the equation y equals the cosine of x. Okay, now we know that if we want to figure out some of these numbers, the best thing that we can do is start taking derivatives. So I'm going to take the derivative of this quadratic approximation. Taking that derivative, I get a1 plus 2a sub 2x. And if we took the derivative of the function we're actually approximating, we would get negative sine of x. All right, let's do it again because we said the second degree would give us that concavity and that's what we're looking for. So taking the derivative again, we'd get 2a sub 2. And the second degree that we're approximating, or the second derivative that we're approximating, would be negative cosine of x. Okay, Now, you'll notice that we started this problem out in the beginning saying that we wanted it centered at x equals 0. Okay, so knowing that the approximation is centered at x equals 0, what I'm going to do is I'm going to substitute in 0 to each of those expressions that I just had or that I just wrote from up above. Okay, so in the quadratic approximation, it would be a sub 0 plus a sub 1 times 0 plus a sub 2 times 0 squared, and I don't really need to write all that, it's just a sub 0. Likewise, if I plug in 0 to that function, the derivative, all I would get would be a sub 1, and the second derivative, all I would get would be 2a sub 2. Now, let's plug 0 into the function we're actually approximating. Y of 0 would be the cosine of 0, which we know is 1. Y prime of 0 would be negative sine of 0, which is 0. And then y double prime of 0 equals negative 1, because it would be negative cosine of 0. Now, I've just created a system of equations. I'm going to link, and I'm going to compare a sub 0, and it equals 1, a sub 1, which equals 0, and 2a sub 2, which equals negative 1. So using the table, we know that a sub 0 is 1, a sub 1 is 0, and a sub 2 is negative 1/2. Okay, so if I were to write a quadratic approximation for y equals cosine of x, what we have is this polynomial, I'm going to give it a name, p of x, equals 1, that's my a sub 0, plus 0x, because that's my a sub 1 times x, plus negative 1/2 x squared. Let's simplify that. Let's clean that up. So that would be 1 minus 1/2 x squared. Okay, let's sketch that graph. I'm going to go ahead and sketch that one in purple just so you can see the difference. But if we graph 1 minus 1/2 x squared, it's a parabola that's upside down, starting at the vertex would be at 1, 0, 1. And then my next point is going to be somewhere right about here. And this parabola looks like this. There's what my parabola looks, something like that. I didn't sketch it perfectly, but this would be that y equals 1 minus 1/2 x squared. And you can see that this parabola here approximates maybe a few more points. Maybe it goes just a little bit further out than 0. Maybe it's to 0.1 and negative 0.1 where we can approximate the points, but it's more than it was when it was just x equal, or the line y equals 1. So what do you picture happening? And we talked about it up above. If I start creating a polynomial that has more terms, wouldn't we expect this curve to be better approximated? Let's try with a 4th degree. So I want you to hit pause and try a quartic approximation. We already did a quadratic approximation. Let's try a quartic one. So hit pause and try it. All right, hopefully you've had a chance to try this quartic approximation. So I'm going to go ahead and quickly fill in the table, or I'm going to start the table, and maybe if you see a pattern you didn't see it before, you can hit pause and try it again. This would be a sub 0 plus a sub 1 of x plus a sub 2 x squared plus a sub 3 x to the third plus a sub 4 x to the fourth. And I'm approximating, in this case, y equals the cosine of x. So if you didn't feel comfortable starting it before, go ahead and try it, hit pause and try it now. Otherwise, come back. I'm going to go ahead and fill these all in for you, and you can check your work. All right, filling in this table, we have this quartic approximation that we continually take the derivatives of. And then the function we're approximating, which started out as the cosine of x, and if we continually take the derivatives, we know that as we get to that 4th derivative, we cycle back into that, back to cosine of x. All right, so since we were looking at it centered at 0, Let's go back to plugging in f of 0 in each of these approximations and see what we get for our coefficients. Okay, as I go back through and substitute in, when I substitute in f of 0, I get a sub 0. F prime of 0, I get a sub 1. And you can see the pattern that's happening here. All those x terms go away. And the function we're approximating from above would be the cosine of 0, which is 1, negative sine of 0, 0, negative cosine of 0 is negative 1, sine of 0, 0, cosine of 0 is 1. And then if we solve using a system of equations, a sub 0 equals 1, a sub 1 would be 0, 2a sub 2 would be negative 1, which means a sub 2 would be negative 1 half, 6a sub 3 would be 0, 24a sub 4 would be 1, so a sub 4 would be 1/24. Now, if I write this polynomial, what we get is we get this polynomial of 1 plus 0x minus 1/2 x squared plus 0x cubed plus 1/24 x to the 4th. And so if I simplify that, my polynomial would just be 1 minus 1/2 x squared. That should look familiar. We already did this. And that was the one we saw when we were doing the quadratic. Well, now we're doing a 4th degree, and we notice that this is the next term that I'm adding. So I'm adding another term to it. Do you think, knowing that this was the 2nd degree, we'll talk about the polynomial, what that means, and this is the 4th degree or quartic approximation, do you think you could find one for a 6th degree approximation? Hit pause, try it, talk to a neighbor, talk to somebody, and see if you could come up with that. All right, see if you had a chance to come up with this. I'm going to give you a little bit of a hint. This expression right here, 2, is equivalent to 2 factorial. This expression is equivalent to 4 factorial. Do you see any patterns? If I were to come up with the 6th degree polynomial, I would include for sure the first degrees that we already did. We'll put factorial there. And my guess is this would be negative 1 over 6 x to the 6th. Notice all my odd term were going away. I don't have any x, like I don't have x cubed. I'm not gonna have x to the 5th. Can we come up with a general expression, a general form for any coefficient? If you were to come up with a general expression for any coefficient, what I hope you would notice is that we took the derivative, so I'm going to use that little symbol, whatever the derivative was, the nth derivative, we did a 2nd derivative, we did 4th derivatives, and we evaluate it at that point. Whatever the point is, we happen to do it at 0, divided by the number factorial would be the general term. I would like to show you a visualization of a Taylor polynomial and how, as we start going, this will approximate the graph more and more. So here's what this looks like. We have this graph, f of x equals the cosine of x. And as we go through this, let's go a little bit slower. There was the first one when we were doing just the basic tangent line approximation. And then we went to the 2nd degree and we created that quadratic. And we didn't graph this, but there would be my 4th degree. And there's the approximation of the 6th degree. And you can see that as we go further and further out and we create this polynomial, the curve starts to model that cosine curve more and more closely. Okay, that's a Taylor polynomial. Now, a Taylor polynomial can go out to, we went to the 30th degree. That's huge. Would we want to write that? Not necessarily. But you can see that as we start peeling degrees away, the approximation becomes not as close to the curve. And as we start adding levels to it, it gets closer and closer to. Now, we didn't really talk about this, but one of the things that we can do, or we haven't talked about it yet, is change the center. I could change my center to be, let's say, for example, let's change my center to be 1. Well, 1.2 is looking good. 1.5, great. And as we start going, my polynomial starts to look a little bit different because it's centered at that 1.5. And we'll talk about how to build that. So let's look at the general definition of an nth degree Taylor polynomial. All right, this general form says that if f has n derivatives at x equals c, then the polynomial is f of c plus f prime of c x times x minus c. Oh, that x shouldn't be there. Okay, cross off that x. I need to change that in my notes. All right, times, or plus, sorry, the second derivative evaluated at c divided by 2 factorial, x minus c squared, plus, and then we continue that pattern on until we get to the nth derivative evaluated at c over the n factorial times x minus c to the n. Now this number c is what we call our center. This number c is what we call our center. So let's highlight that and just make note of that. So this x equals c right here, all of these c's that are in here represent our center. So c equals the center, meaning that's where we're starting to build our polynomial from. And this is called an nth degree polynomial, or Taylor polynomial after the English mathematician Brooke Taylor. This is an nth degree polynomial. And so you'll see that notated in the subscript, and you'll see it notated as we go towards the nth term that we're trying to find. So we just looked at a 6th degree polynomial, we looked at a 4th degree polynomial, or we made a guess at a 6th degree polynomial, we looked at a 4th degree polynomial, we looked at a 2nd degree polynomial, we also looked at a degree 0 polynomial, which was that horizontal line. Now, if we have a series that happens to be centered at 0, okay, if the series happens to be centered at 0, this particular polynomial, or this series, has a specific name, and this series is called the Maclaurin Series. So Maclaurin simply means that it's centered at 0. So rather than, I have a typo here too, darn. Rather than having this c here, this c will always be 0. So we could just write x minus 0, x minus 0, x minus 0. That would be a Maclaurin polynomial, or Maclaurin series. All right, so let's look at what it actually looks like to write an nth degree Maclaurin polynomial. Remember, this expression right here, this Maclaurin polynomial, simply means that the center is 0, is when x equals 0. So let's write a Maclaurin polynomial, and I'm going to base it off of what we just did. Yes, we already know this. We know 6 terms of this so far. But I want to look at what it looks like in general. How do we use that formula that was given to be able to write a polynomial? And that's what we're going to look at here. So the first thing I'm going to do is I'm going to start by taking derivatives. And I don't necessarily need too many. Hopefully you start to see a pattern that happens. So really we just need as many terms as it takes to develop a pattern. So here's what I'm going to do. The first thing I'm going to do is I'm going to start with the function that was given. That was f of x equals the cosine of x. And I'm going to start taking derivatives. So the first derivative of this would be negative sine of x. The next derivative of this would be negative cos x. The next derivative of this would be sine of x. And I'm going to take one more derivative, just so I can see the pattern. of what's happening if I took this next derivative. The derivative of sine of x is cosine of x, and I'm back to where I started. What I'm also going to do is I'm going to take and evaluate each of these expressions at the center point. Well, my center point is 0, so f of 0 would be 1. F prime of 0 would be negative sine of 0, which is 0. F double prime of 0 would be negative 1. The third derivative evaluated at 0 would be 0. And the fourth derivative evaluated at 0 would be 1. So if I start building this series, I'm going to call it P sub n of x because I don't know how many terms I'm going to go out. And I'm going to start by filling in the formula. And remember, the formula said, using the Maclaurin, it said that we're going to take f of c, and our c is 0, plus f prime of c times x minus c, plus f double prime of c over 2 factorial. This would be over 1 factorial, I just don't need to write it, times x minus c squared, plus, and I'm going to keep going until I do f, the nth derivative evaluated at c, over n factorial times x minus c to the n. So let's look at what that looks like. For us, f of c, right here, f of c was 1. So this first term will be 1. F prime of c was 0. So this next term will be 0 over 1 factorial times x minus 0 because our center is 0, plus f double prime, which was negative 1, over 2 factorial times x minus 0 squared, plus, let's keep going, my next term was 0 over 3 factorial times x minus 0 to the third, plus, and my last term that I worked on was 1, the derivative was 1, over 4 factorial times x minus 0 to the fourth. Let's clean that up just a bit and see what that actually looks like. Cleaning this up a little bit, I get that this polynomial would be 1 minus 1 over 2 factorial x squared. That next term goes away because it's 0 over 3 factorial, which at times something else is just 0, plus 1/4 factorial x to the fourth. And we already said we could guess terms. Our next term that we would have guessed would have been 1 over 6 factorial x to the sixth. The next term would be 1 over 8 factorial x to the eighth because it's these alternating evens. Well, how do I write that? Let's think about what we know. What have we done with series so far? If I say alternating, what do you think? We think of negative 1 to the n power. Now, does it alternate in the right way if we choose negative 1 to the n power? It does if we start at, we want the first term to be positive. So if we start at 0, that part will work. And then notice the numerators every time is 1, but that 1 is related to just the coefficient. And then what we have here is, and I don't need to write with the 1, then I have x squared, x to the fourth, x to the sixth, x to the eighth. But here's what happens. I get x squared on that second term. So I'm going to call this x to the 2n over n factorial. Oh, 2n factorial, sorry. 2n factorial. Here's why. If I plug in 0, I want to be able to get 1. If I plug in 1, my next term, I want to be able to get the expression 1 over 2 factorial x squared. So if I plug in 1 right now, do I get a negative? Yes. I get x to the 2 power, and then I get 2 times 1 factorial. That gives me that term. If I plug in 2, I want to be able to get this term. So this expression here is when n equals 0, when n equals 1, when n equals 2, when n equals 3, when n equals 4. And that's how I get those expressions. So this is really just a series, an alternating series, that has this expression here. There's an nth degree Maclaurin, because it's centered at 0, polynomial for the cosine of x. If I take the sum from 0 to infinity of that alternating series, I will recreate the cosine of x. All right, so here's what I would like you to do. Hit pause and see if you can come up with the terms for a 5th degree. You could just go 4, I'm fine with 4. 4 degree, no, go 5th. Go 5th. 4 doesn't work. 5th degree Maclaurin polynomial, so it's centered at 0. See how you do. All right, first thing we should do is take all of our derivatives. So we're going to start with f of x equals the sine of x. And I'm going to start taking derivatives. So first derivative is the cosine of x. Second derivative is negative sine of x. Third derivative is negative cos x. Fourth derivative is sine of x. We asked for a 5th degree, so I'm going to keep going to get cos x. And now I'm going to evaluate each of those at the center. So f of 0, f prime of 0, f double prime of 0. Handwriting's getting worse. Okay, so evaluating each of those, I would get, let's see, sine of 0, 0, 1, still 0, negative 1, 0, positive 1. Great. Now to go for my 5th degree polynomial. So p sub 5 of x. This is going to be the polynomial that best approximates the sine of x. So first term is 0. The next term is 1 over 1 factorial x to the first. The next term is 0 over 2 factorial x squared. The next term is negative 1 over 3 factorial x to the third. The next term is 0 over 4 factorial x to the fourth. And then the last term is cosine of 0 is 1. Yeah, we're good. Yeah, okay. Is 1 over, 5 factorial x to the fifth. I thought I'd made a mistake. All right, let's clean this up. So I get 1x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. And if we go back to this 1x, maybe we rewrite it the same way we had it, 1 over 1 factorial x to the first. There's my 5th degree polynomial that models the sine of x. Okay, so can we come up with a general expression? Can we come up with a sum? What do we see? Well, we see that it alternates. So let's do negative 1 to the n power. And then we see that the powers we have are all odd. To have odd powers, I'm going to do 2n plus 1. 2n plus 1 means odd. And I notice that all my factorials are odd as well. So I'm going to divide this by 2n plus 1 factorial. This is the general expression for the Maclaurin polynomial that models y equals sine of x. All right, let's try another one. Hit pause. If that one caused you some grief, maybe now you can try this one and be good at it. Let's hit pause and try writing an nth degree Maclaurin polynomial for f of x equals e to the x. All right, this is the best one. Why? Because all my derivatives are e to the x. Makes life really easy, which means evaluating each of them at 0, is 1. So if I go to write this polynomial, and we're going to write an nth degree, my first term would be 1, because that's f of 0, plus 1 over 1 factorial x to the first, plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, plus 1 over 4 factorial x to the fourth. We didn't even do that many terms, but that's what would happen. We just keep going. So could I come up with a general expression that represents this entire series? Again, I'm going to start at 0. Is it alternating? No. How are my x's behaving? Well, I'm going to keep going up by the letter n. So it would have x to the n over n factorial. And this would be the series, the Maclaurin series, that represents the polynomial that represents f of x equals e to the x. So these three forms that we just looked at, these three general forms, we're going to call this the general form. The general form is the one, I don't know why I wrote it in highlighter, general form of a Taylor or Maclaurin polynomial is the sigma notation. Those three polynomials that we just wrote, you either need to memorize or you need to know how to find well, because they come up the most. Sine of x, cosine of x, and e to the x are our Maclaurin polynomials that come up a fair amount. Okay, so what happens if it's not centered at 0? The last three that we looked at were all Maclaurin polynomials, meaning they were centered at 0. What happens if it's not? Let's look at an example. Suppose we have a function that has continuous derivatives, meaning I can take a first, a second, a third, a fourth, a fifth, a sixth, a seventh, and it keeps going on forever. I can take all the derivatives. And that we have this information that f of 2 equals 1, f prime of 2 equals negative 3, f double prime of 2 equals 5, f triple prime of 2 equals negative 7. What it's asking me to do is write a Taylor polynomial of degree 3, meaning the highest exponent I need in there is a 3, for the function, I don't know what the function is, but for a function, and it's centered at 2. This centered at 2 part's important. You'll notice that every expression that we had was evaluated at 2, kind of like we did up above with f of 0 in each of those examples. This one's centered at 2. So if I write an expression for this polynomial, my p sub 3 of x would be f of 2, according to Taylor, plus f prime of 2 divided by 1 factorial x to the first, oops, I didn't do that right, x minus 2 to the first, plus f double prime of 2 over 2 factorial times x minus 2 squared, plus f triple prime, evaluated at 2, over 3 factorial, x minus 3, oops, not x minus 3, x minus 2 to the third, plus, and I would keep going, except that's all that I was given. A couple things you should notice when you're writing a polynomial like this. This number here, the factorials, will always match the degree. So if I'm in a 0 degree, this is a 0 degree, it'd be over 0 factorial, which is just 1. So we don't write it. First degree, 1 factorial. Second degree, 2 factorial. Third degree, 3 factorial. And you'll notice also that the derivative matches the n value that we're at. Okay, well, let's fill in the information that we were given. So my polynomial here would be f of 2, which we said was 1, plus f prime of 2 is negative 3 over 1 factorial x minus 2 to the first, plus my second degree evaluated at 2, or second derivative evaluated at 2 is 5. And my third derivative evaluated at 2 is negative 7 over 3 factorial times x minus 2 to the third. Factorials don't really look like factorials. Now, I could simplify this just a little bit, and I could combine these, but really I just get 1 minus 3 times x minus 2 plus 2 factorial is 2 times 1, so this would just be 5 halves, minus, this would be 7, 3 factorial is 6, x minus 2 to the third. So this is the polynomial that models or is approximately close to some function. We don't know what the function is, some function f, but this is the polynomial that models it. All right, so the rest of the examples that we have for this are on separate videos. So go ahead and watch those, and we will talk to you soon.